Hello, my name is Kees Snoek. I'm from the University of Amsterdam, and I'm happy to fill another slot in this tutorial on multimodality learning from videos and beyond. And I have as my title today, Video, Multimodality, and Similarity. It's always good to look back and see what we have achieved as a community. So this is a video that accompanied the C3D work from Dutronatol at Facebook. It's already a while ago, but it shows very convincingly what we can do in trimmed action classification. So for each video, you will see what is the most likely activity that is happening according to their methodology. And as you can tell, often the number one pick is indeed correct and very convincingly so. And even the runner-up classes are also often very relevant. So this is already in 2015, we could do this very well. Here's another example of segmenting an actor and an action based on a lingual description. So here the goal is to identify the woman in the purple dress who is running, and identify all the pixels that belong to the actor and the action. So this is a very reasonable result given that it comes from a sentence as input. And the nice thing about this algorithm is that when you change the sentence and keep the video the same, and all of a sudden we are looking for the gray dog who was running on the leash during the same dog show, then the algorithm can figure out that it is indeed, those are the pixels that belong to the gray dog. And while this may appear simple, note that there are many other dogs also in the background visible. So the algorithm has really figured out that this is the dog of interest. Here's another recent achievement. This is work from my team that appears at ICCV this week. And here we consider the problem of video relation detection, where the goal is to detect an object, a subject, and the predicate. And to do so by putting a tube or a box around the objects of interest. So here we find the adult, we find the horse, and we also find the predicate that is happening. So in this case, the adult cleaning the horse. And also on this rather new type of problems, a lot of progress is being reported lately. Now, I think the driving force behind all this is, of course, advancement in deep supervised learning. So when one composes a closed world data set, or I would say a rather closed world, and adds lots of labels to videos of interest, let's say action classification, and you add class labels, then with deep learning, you can really get fantastic results. So results will be state of the art. You can impress your audience, but it still will be a relatively closed world. The goal of video understanding eventually is to move into a real world, and people are actively pursuing this quest, and we are slowly moving into this direction, attacking more and more complex problems that we can infer from video signals. But here there's also a problem, which I like to refer to as the video understanding paradox. And the point here is that as understanding becomes more and more specific, it is very unrealistic to assume that sufficient examples to learn from will be commonly available. So here you see frames from a video where somebody is trying to steal a bike in New York City. Now you can imagine that at some point you will build a detector that can identify bike thieves, that scans the street in front of your house to see whether your bike is still there. The problem here is that it will be hard to collect sufficient examples of actors performing the act of interest, because of course the thief does not want to be caught on camera. So it will be very hard to find sufficient examples to build such a detector. Not to mention the fact that you also still have to label each individual box in all the frame for a large variety of actors and thieves performing a similar activity. Or maybe you're also interested in pixel level segmentation, and you need to label every pixel in all the frames. And again, for a huge diversity of videos. Or perhaps you're interested in causality to infer, hey, if somebody's walking around on the streets with a crowbar, maybe this is indicative for an activity that is bound to happen. All this requires huge amounts of annotations. So it is pretty clear that moving along this direction for video understanding in the real world, which is highly dependent on supervision, is a dead end. Not to mention all the ethical and computational constraints that come with it. So the mission should be to have real-world video understanding, which is not as dependent on supervision as today's methodologies. Now, this is a big topic in the field, and there are lots of angles to approach it. So some recent developments in machine learning, most notably self-supervised learning, where the inherent structure in the data is exploited as a label to learn from, very effective. Meta learning that tries to learn not only a single task, but tries to infer from multiple tasks what is the best tactic to address similar tasks in the future. Another interesting line of research is domain generalization, where one has seen a certain class in different source domain. Let's say you have seen an elephant in photos, in art paintings, and in cartoons. And then the goal is to build a classifier that can still infer the classifier on unseen target domain. So all of a sudden, you see a sketch that has never been seen during training, and the task is to still be able to recognize the elephant in this sketch domain. So these all really help towards making methods more robust and eventually also much more data efficient. And we are seeing some work that trying to combine multiple of those techniques, like few-shot domain generalization, work from my team at ICCV last year, where we combine domain generalization and meta learning to learn classifiers for only a few shots of examples, and which are still able to generalize to unseen domains. Okay, but today I want to talk about another topic. So in reaching the mission of real-world video understanding that is not less dependent on supervision, today's topic is multimodality and similarity, and I will discuss those two topics based on two recent papers from my team. So first, I would like to talk about motion similarity, and in the second part, I will cover also audiovisual similarity. So for motion similarity, we're looking into a paper that appears this week at ICCV. It's called Motion Augmented Self-Training for Video Recognition at Smaller Scale by Kirill Gavrilyuk from University of Amsterdam, together with Mihir Jain and Ilya Karmanov from Qualcomm AI Research. And in this paper, we set ourselves the following goal. We want to self-train a model that can be effectively fine-tuned on small-scale datasets with around 10,000 videos. And it is well known that such small-scale video datasets benefit much more from motion than appearance. And the reason is that there is too much information in the RGB to learn from with only a small set of small data set, and the much more sparse flow signal is much more informative. But flow has a downside, and flow computation affects efficiency, which is often what you don't want if you're in a small scale scenario on a compute budget. So we set ourselves as a goal to train a network using optical flow, but avoid computation of the same flow during inference. And I will explain how that can be done. So the standard tactic in problems like action classification is to take a hugely labeled data set, let's say the latest version of kinetics. You train your favorite CNN, and you try to predict trimmed clips that come with an associated label that has been provided by human annotators. Now, by doing so, you learn a network with reliable weights, good initialization, and then when you move to a a new data set, let's say UCF 101, a small scale one, you use the same network architecture with the pre-trained weights, and then you start to fine-tune those weights further with additional annotations that have been provided on this additional data set. Now, the shortcomings of this approach are rather clear. It requires large amounts of human annotated videos to pre-train. Also, it treats different video representations like RGB and flow, and also audio for that matter, mostly equally. So the contributions we're making here is an architecture we call motion fit. So this is a motion augmented self-training procedure. And what it does is transfers optical flow information to an RGB model via a self-training procedure on unlabeled video data. We've presented an empirical study to discover what form such video pseudo-labels should take at a smaller scale, and we will demonstrate that this can really boost accuracy on small-scale video data sets. So the motion fit model works as follows. We have a small data set from which we extract optical flow motion representation. Then we train a motion model using a small amount of human labeled classes. Let's say some action classification problem. Let's say we do some action classification on UCF 101. So based only on the flow information. And doing so, we learn the fine motion changes rather than repetitive and abundant appearance details that may appear in background and so on. We introduce a multi-clip loss, and this is essentially splitting the trimmed video into multiple short clips, and we assign the video label to each of those clips, and we try to optimize in this way. The idea being that the action of interest may happen only in a part of the video, or be really emphasized in a small part of the video. And by learning it in this way, we better capture the fine and descriptive details of the optical flow. So we really capture the foreground information, so to say. Okay, this is step one, and this gives us a what we call a motion pseudo-label generator. So a model that is trained on optical flow only. Then we move to a big source data set, let's say kinetics, but here we don't use the human annotated labels. So we just use a large amount of video. We again compute the same optical flow features on this data set. And then with our pre-trained model from step one, we start to extract features from this large video data set. Then we introduce different ways of temporal modeling of those features. We cluster them just using simple Euclidean k-means with Euclidean distance to obtain pseudo-labels. Then we turn our attention to the same data set, but then extracting appearance features. We use an appearance network of our likings. And what we then try to do is use the pseudo labels obtained from the motion branch and try to predict for each input clip how well it can predict this pseudo label. And again, using the multi-clip loss. So we consider 3 levels of temporal granularity here. So clip, segment, and video level, where segment can be some semantic identification of temporal extent. So the pseudo labels are obtained after k-means clustering of the motion features from this data set, the source data set, and then we are trying to predict it based on appearance. So this is where the motion augmentation happens, so to say. Interestingly, we do not need to use the same architecture. So for the flow features, we can use a different network architecture than for the RGB architecture, because they act on different streams. The only thing they have in common is that this one tries to create clusters of pseudo labels, and this one wants to predict those pseudo labels. Then we can change our attention to downstream tasks. So we have a small scale target domain. We extract appearance features. Then we apply our RGB model that we trained in step 2. And we have, again, with this data set, a small amount of class labels for which we then can fine tune our model to the task of interest. Let's say action classification or clip retrieval. Okay, so this is the basics of the model. And what I have now shown is how you can augment an RGB appearance model using optical flow in a self-training way. So on this big source set in the middle, we don't need any labels. That is the main benefit. So here are some implementation details for the experiments I'm going to detail. So it is well known that both UCF 101 and ACMDB 51 are too small for their direct training of a 3D CNNs on RGB information only. So we use those, we use UCF 101 as our source set for the motion pseudo label generator. We extract TVL1 optical flow, and we train a model here on the R2+1 D18 layered backbone from Dutran et al. From CVPR 2018. Then for step 2, we rely on Kinetics 400, but without its human provided labels. We extract, again, the optical flow and also the RGB features. And for the optical flow, we again rely on the R2+1 D18 backbone. And for the RGB network, so this one over here, we vary between 2 backbones, the same one that we use for the optical flow, but we also explore an S3DG network by Chi et al. From ICCV 2018. And here again, the small scale data sets on which we report are UCF 101 and ACMDB 51. So here is our first ablation study that shows the benefit of this motion representation on UCF 101. So we directly train a model here on UCF 101 training set, and we report results on the test set to show the benefit of having a motion representation versus an appearance representation. And as you can see from those results, when we train on motion on this small scale data set, it is really much better, up to 30% better than appearance for the settings that we evaluated. Now, then we have this multi-clip loss, where we separate each individual video clip into 1, 2, 3, or 4 subclips, each covering 16 frames. So as you can see is that multi-clip training is even better than using a larger input temporal extent. So for example, compare the 32 clip, the 64 clip length over here, which scores 81.1 in terms of motion representation. And if we have only 2 clips already, which is 32 frames in total, we surpass this 64 frame clip length. So this multi-clip loss is effective too, and we recommend to use three multi-clips. Then we also ablated the motion augmented self-training. So here we looked into what is the temporal granularity that we should use to create these pseudo labels. So we used an entire video. We also tried action bytes from work from CVPR 2020. We tried TSN, temporal segmentation network, that scores 77.3, and we also did the multi-clip based approach that we have been, the simple approach. And interestingly, this beats the more advanced semantic partitions of a video, as well as the regular video level. Then we looked into the number of clusters to pick for the pseudo labeling. and also what is the influence of the amount of data, unlabeled data that is available to create the clusters. Now, what we found is that motion fit is not so sensitive to the number of clusters. So as you can see, moving from 128 till 1600 clusters does not change the results too much. In fact, here it even starts to deteriorate, probably because of overfitting effects. But in general, we see that 128, we don't see much benefit beyond 1,000 clusters. Of course, providing more data for the clustering is beneficial. So when we switch from the kinetics validation set to the kinetics training set, which is a factor 5 in amount of data, one can see that the results get a good jump. Then we compared our motion augmented self-training procedure with other motion knowledge transfer approaches. So we compared with MERS and MARS, and these are supervised approaches. So we adapted them to our setting. And where you can see is that our approach outperforms these approaches by a good margin on both UCF 101 and HMDB 51. And more interesting is that we are even outperforming other knowledge transfer methods that rely on additional ImageNet labels. So we get a good results here. Here's another comparison against self-supervised work, where we compare against multimodal and vision-only self-supervised approaches. So on the top are the multimodal works, and in the green box, the vision-only approaches. And what you can see is that motion fit, even when using exactly the same backbone, number of frames and resolution, outperforms most vision-only methods. So we are state-of-the-art on UCF 101 and competitive on HMDB 51. And interestingly, we are also on par with several of the multimodal approaches. So this essentially shows that there's a lot of promise to also include other modalities in the motion fit regime. We saw the same behavior for clip retrieval as a downstream task. I'm not going to show the table, but I'm going to show you some success and failure cases. So here are the queries, and here are the top 3 retrieved videos. So green indicates we found a correct clip, and red indicates that we found a wrong clip. So essentially a clip that belongs to a different action class. It is interesting to look at the failure cases over here, where we notice that while our model may retrieve videos from different action classes, it still somehow captures distinctive motion patterns like hand motion and human poses that RGB only models cannot capture. So conclusion for part 1 on motion fit. It transfers motion similarity to an appearance network via a self-training procedure. It does not require costly optical flow computation during inference, just RGB, but you will get sort of like the augmented flow for free. And it is especially well suited for deployment on small scale video with compute budgets. All right, that concludes part 1. So now I would like to move to part 2, where we're going to look into audiovisual similarity. And this is work from CVPR this year, together with Yunhua Zhang and Ling Xiao. So here we look at repetitive motion, and visual repetition is actually a very interesting phenomenon that is ubiquitous in our world. It appears in human activity like sports and cooking, but also animal behavior like a bee's waggle dance, natural phenomena like leaves in the wind, and also in urban environments like flashing traffic lights. And estimating such visual repetitions is, from realistic video, is really challenging. Now, many people in vision have attacked this problem. So we found papers that are easily dated 20 years, are easily 20 years old, and probably there's more if you dig deeper. And what people have done in those, I would say, early days, is to represent the video as a one-dimensional fixed period Fourier signal that preserves the repetitive motion structure. Now, for such a strict assumption to work, they had to assume that the video they are working with was static and stationary, because it's basically inapt for an open and real world. So here you see that exemplified by a video of a rower who is all of a sudden accelerating. And this is plotted in the time frequency space over here. So there's an acceleration of the rower. And this appears as a shift of the maximum power in the time frequency space. And the Fourier transform is unable to handle such non-stationary motion. Now, for the non-stationary world, we have worked on wavelet transforms of optical flow features. And how did we go about? We first segment the foreground motion. So that is the top row with the blue segments. Then we compute some optical flow, the yellow arrows that are visible. We extract several 0th and first order flow signals, and 4 of them are shown over here. And finally, we decompose them all into a time frequency spectrum using the continuous wavelet transform. And then in the bottom row, you can see a dashed black line, which denotes the minimum cost path, and an orange line indicates the maximum power path for counting by integration. And by doing so, we could count the number of repetitions in video, including non-stationary videos. Now, this is using rather traditional signal processing techniques, and we published this in CVPR 2018, and in years after, in CVPR 2022, works proposed a deep learning-based solution to repetition estimation in video. And of course, what is needed is large data sets. So 2 data sets were proposed that year at CVPR. One is CountX by folks at DeepMind. And the other one is by Zhang et al., who introduced UCF-Rep as a sort of like an additional annotation on top of UCF 101. So the data set here comes with, let me play it, with repetitive actions together with the count. So how often does a repetition repeat itself in a video clip? And because this large-scale data set now all of a sudden was available, of course, deep learning can show its power. Now, here are some video examples that are hard in repetition estimation. So I will show you some example. So these are real-world challenges that appear once you take in a classifier out of its training environment and let it go in the real world. So the first one showed low resolution. This one shows a person on a trampoline in the dark. This is a tennis match, and we are counting the repetitions of the tennis players, but all of a sudden the actor of interest appears out of sight. So this is very challenging for visual solutions, and this is the effect of camera motion. So how can you still count the number of repetitions when the camera follows the ball? Very cluttered scene, so very complicated where to look. This is also an interesting one. The scale of the swimmer changes. And last but not least, a very fast motion, so very hard to count precisely the number of repetitions that are happening. So we reconsidered this approach, and we make 3 contributions. So we looked at video repetition estimation from a new perspective based on not only the sight information, but also the sound signal that accompanies a video. We proposed the first audio-visual model for repetition estimation in video. And to further facilitate research in this direction, we reorganized and repurposed two sight and sound datasets for video repetition estimation. Now, this is the basic model. So from the highest level, it has a sight stream, which is simply an S3D net that predicts counting result per input clip and repetition class. And repetition class is a sort of like latent number of classes that are optimized during training, where you try to fit a video into one of these latent classes and then predict the number of repetitions. The idea being that different activities show different behavior. We do the same for the sound stream, but here we use a ResNet 18, predicting the counting results per sound spectrogram. And again, using this latent repetition class. Then something that is special for this architecture is the temporal stride module. And what this does is that it selects per stride, or the best stride per video for the side stream based on visual and audio features. So the number of repetitions varies per video, and one can use the audio information to estimate what is the best temporal stride to capture a cycle of a repetition so that you can recognize it well. And then last but not least, we have a reliability module that decides what prediction to use, so whether to rely on the sight or the sound. And this is especially useful when the visual circumstances are too bad to make a reliable decision. This is the global overview of the model. This is the slightly more involved version of it. I think I'm going to skip going over all the implementation details. There is a QR code on the top right, where you can find the accompanying source code for the model. Okay, we also repurposed and reorganized the Countix dataset as proposed by DeepMind at CVPR 2020. And we selected for the Countix audiovisual version about 1900 videos covering repetitive activity categories with clear sound and without background music, so that we had a real good set to evaluate the value of sight and sound, with an accompanying train file and test partitioning. We also created a test set, a challenging test set, which we call Extreme Countix Audiovisual. And this dataset contains 156 videos from Countix AV and another 58 videos from the VGG Sound dataset, in which the sight conditions are too poor for counting, so that we really force the model to listen to the sound. Now here you see some samples from this dataset. I will show some more videos at the end as well. So first we are ablating the benefit of the different model components, and we are reporting the mean average error. So we are predicting how often does a count repeat itself in the video, and we compare this with the ground truth and report the average error. So the lower the mean average error, the better. So for the sound stream, for the sight in the sound stream, we see that the sound by itself is worse than sight. If we add sight with a temporal stride, which is also using the audio features, the mean average error gets reduced a little bit more. Then for the fusion, we could rely on simply averaging the predictions of the sight and the sound stream, but we found that having this reliability module lowers the mean average error a little bit more. So all our modules matter, and the reliability estimation is preferred over simple averaging. Now, then we have a big comparison table where we compared our model with the ones that have been published in the literature. And what we can see here from this table is that on the site-only datasets, our site-only model already outperforms all the state-of-the-art models for both UCF, REP, and Countix. When we rely on sound only, that is not really competitive on these site-dominated datasets. But if we combine sight and sound, also on Countix results further improve. Now, more interesting is to look at the sight and sound datasets, where we see slightly different behavior. So the Countix AV dataset is really a dataset where sight and sound are treated equally, because we know that the sight conditions are quite reliable, and also the sound conditions are reliable. So this, again, it shows that sight by itself is better than sound, but if you combine the two, you get a benefit. And then in the extreme Countix dataset that is really optimized for poor vision conditions, but reliable sound, we can see that sound all of a sudden starts to outperform sight, and again, the combination reduces the error. So let's dive a little bit deeper in this extreme Countix AV dataset, because we also separated this dataset according to several real-world challenges. So, for example, we identify those videos that have a huge camera viewpoint change, or a very cluttered background, a low illumination, fast motion, disappearing activity, scale variation, low resolution, and so on. And what we see here is that sound is much less sensitive than sight for these visual challenges. And the combination of sight and sound always outperforms sight only. So that is, I think, an interesting observation. And now let me show you some videos together with the sound. So here you see the video, here the prediction of the number of repetitions given the sight stream, the sound stream, and their combination, as well as the ground truth. So this is a low resolution video, but the sound is quite reliable. Somebody turned off the light, but the trampoline jump has a very characteristic sound. And despite this actor walking away out of the camera view, the sound continues as usual. Camera motion has no effect on sound. And also the visual clutter is ignored by the sound. So does film. Fast motion, and the sound can still figure it out. So that brings me to the end of today's talk. Real-world video understanding with limited supervision is really a grand challenge. And in this talk, we highlighted only two aspects of interest. So one is motion, and the other one is audiovisual similarity. And interestingly, they are all both naturally embedded in learned representations. So there is really a benefit. You can still learn reliable representations also using data efficient methods. And I really believe we have only started to explore the opportunities of this exciting problem. So with that, I would like to thank you for your attention. And should you have any questions that you would like to ask me, please contact me via the following means. And with that, I would like to close, and thank you, and enjoy the rest of this tutorial.